Okay, so here we have a function, f of x equals 4x squared minus 3x plus 4. It wants to find f prime of 3, so that's not bad for us. So f prime of x, bring down the 2, that would be 8, subtract 1 from the power, minus, and this is 1 power, bring it down, 3, subtract 1 from the power, that x is gone, and the 4 is just 0. So there we go, and now f prime of 3, so if we plug in 3, it's 8 times 3 minus 3, 24 minus 3 is 21. So that's how we got the 21. Okay, then it says use this to find the linear approximation to f of x at x equals 3. So what are they talking about? The equation of this linear approximation is this is going to be the equation of the tangent line. Now, what's a tangent? Let's make sure we're clear on this. Here we go. I've got a graph for you. So here's the situation. So here's this is graphed on the Desmos graphing calculator. Here's the original curve, this red curve. You know, it's an x squared curve, so no surprise. It's a U shape, right? It's a parabola. Okay. And then over here's the tangent. We're about to find that tangent line equation. I graphed it on the same thing. See, they intersect around right here. They intersect. What is a tangent line? A tangent line again is a straight line, right? This is a linear equation, meaning x is only to the first power. Linear equations and lines, x is to the first power. This is x squared, so U-shaped parabola. Anyway, so it's the line, tangent line is a line that barely nicks the graph. In fact, I'll tell you where they hit. They hit right there at over 3 up 31. We'll find that in a minute. I'll show you how we can find that x and y in a minute. But basically, a tangent line is a line that barely nicks a curve in only one point. And the point of this example is that around there, the blue line and the red line are very, very close to each other, aren't they? You can hardly tell them apart. Now, if you get way over here, then yeah, the blue line and the red line are very different. Or if you get way over here to the right, the blue line and the red line are again very different. But right around where they intersect, right around the point of intersection, and that's what a tangent line means. It's a line that intersects, nicks a curve in only one point, and it has the same slope as the curve right at that point. And the slope of the curve is the derivative. And so the slope of the tangent line is the derivative of the curve there. And so right in that neighborhood, right around where they intersect, they're almost the same thing. The tangent line, the blue line, and the red line are very, very close in that neighborhood. And so in higher math and science, physics, chemistry, engineering, whatever, we use tangent lines as an approximation to the original curve. Why? Because tangent lines are easy. They're just linear equations. They're just x to the first power. They're really easy to do fancy math stuff, derivatives, integrals, and higher stuff to do fancy math stuff with. Whereas the other curves can be difficult. This one's not too bad. It's only x squared, but sometimes in higher physics, chemistry, you'll have really difficult equations and it's hard to do the math stuff with it. So instead, you'll say, hey, look, they're about the same. I'm only going to be in this neighborhood where they intersect. So I'm just going to use, you'll see them do this. I'm just going to use the tangent line as it's approximately the same in this neighborhood. So whatever fancy math stuff I need to do, I'll just do it on the tangent line because it's so easy to just handle a linear equation. And that's what they do in higher math and science. So we're getting you ready for that. We're giving you the tools that they will use in higher math and science. They use tangent lines, which are lines that nick a curve in only one point, and they're linear equations. They're mx plus b, and in the neighborhood of where they intersect, they're very, very close to each other. So coming back up, how do we find? So when it says, use this to find an approximation at x equals 3. It means find the tangent line. All right, so here's the equation. How did they come up with that? Well, they started with this. This right here is the slope. That's the m, right? So we have the y equals mx plus b, right? It's a tangent line equation. It's just x to the first power. We already know the m. The m is 21. Why? Because that's the derivative. The derivative is the slope. So, okay, great. But what's x and y? Well, we got x right here. X is 3. How do we find y? Well, you just go back to the original function. Remember, this is y. f of x is y. So y equals, and then plug in that 3. 3 squared minus 3 times 3 plus, can read the same way as 4. Okay, 4. Does that make sense what I'm doing? I'm taking x equals 3 and I'm just plugging in 3. Boom and boom. And to find out what y is, because f of x is y. Function values are y values. So that comes out y equals, I don't know what. If you work that out, you're going to get y equals 31, I believe. Is that minus 9? Uh, yeah, 31. Y is 31. So your y equals 31. So that means x is 3, y is 31. So that means when I take this equation, I can take m, which I already know is 21, because that's the slope, x plus b, and I can plug in for the y. I should have done that. Plug in for the y and the x. The x is 3, the y is 31. Right? Plug in the y is 31. The x is 3, and we can solve for b. 31 equals, this will be 63 plus b. Subtract this 63 from both sides. Boom. So we've got b equals minus 32. So the equation then, so b is minus 32. It's going to be mx, remember it's mx plus b, as we said right here. And now we know the m. We already had the m. The m is 21. So it's 21x. And now we know the b minus 32. So 21x minus 32. That's the equation. They're calling it L of x. It just means the approximation, linear approximation, meaning it's y, it's the tangent line. Now, I know they wrote it like this. That's another version of the same thing. If you multiply that out, you would find that it's exactly the same as this. I'm just going to go with this way. Either way, it's good. So we found the equation of the tangent line. It's not the first time we've done that. We've done that before. So again, take the derivative, plug in 3, you get the slope. Then you got y equals mx plus b, plug in the slope. Then how do you find the x, y? You take that x and you plug it into the original function, work it out to get y, 3 and 31, plug in x is 3, y is 31 along with the slope, solve for b. B is minus 32. So there's b, there's m. We got the equation of the tangent line. Now, so that's this. That's how I got this 21x minus 32. That's the blue tangent line. Okay. And we know they intersect at 331. We found that x is 3, y is 31. Now, use that L of x, that tangent line equation, to approximate f of 3.3. So f of 3.3, when you see this little shaky equal sign, this means approximate, right? It's not exactly equal, it's shaky equals. It's approximately equal to. So approximate to 7 decimal. How am I going to do that? I'm just going to plug in 3.3. That means, here's what I want you to see. At 3.3, where's 3.3? I don't know, maybe this is 3.2, 4, 6, 8, and 4. Yes, 3.3 would be about right here. Yeah, so 3.3 is about right here. So go up to 3.3. Yeah, see right there. They're going to be very, very close. Let me just draw this. 3.3. Right about there. They are super close. You can see that, right? At 3.3, the red and the blue lines are super close. The blue is a very good, this is at 3.3. The blue is a very good approximation for the red. So anyway, that's what we're going to find out. Let's go find that out in particular. So getting back there to the equation. The graph doesn't want to move. Okay, there we go. How we can do that? So it says approximate. Um, Sorry, my thing is freezing up a little bit here. There we go. Hello. All right. So use that linear equation. Use this to approximate f of 3.3. So that means I'm going to plug in 3.3 right there for x. So I get 21 times 3.3 minus 32. Let's go figure that out. 21, 3.3 minus 32. 21, 3.3 minus 32. Go to our Desmos calculator. 21 and 3.3. Was it minus 32? Yeah, there is 37.3. 37.3. And that's, in fact, the answer we get there, 37.3. Now, again, that was, we plugged in that x value to the linear equation, right? So we plugged in right there 3.3. Plugged in 3.3, and y came out to be whatever it did, I don't remember, 37.3. So that means that's the blue. So that means this is the point right here over 3.3 for x, up 37.3 for y. Now, that's pretty close. Now, what's the actual red function there? That's what they're asking us about here now. They're saying, compare this with the actual value, f of 3. This is the actual, they wanted true equals. So that means I'm going to plug back into the original function. So going back to the original function, f of x equals, which is 4x squared minus 3x plus 4. And now I'm going to plug in 3.3 there and there to the original function. 4x squared minus 3x. So 4, 3.3, whoops, times 3.3 squared minus, I'm forgetting, 4x squared, 4, 3.3 squared, minus 3x plus 4, minus 3x plus 4. That's 3 times 3 times. Is it plus? I forget. I think it's plus 4. That's right, right? Yeah, got it. Okay, so what did Desmos say? Desmos said it's 37.66. 37.66. Yeah, that's the answer. 37.66. On the graph, let me show you. So that means on the graph, my graph is just, the red one is just barely above, and it's 3.3 over, up just a little bit higher. See how it's just a little tiny bit higher than the green, right? The red function is barely above the blue function there. They're both over 3.3, right? But at over 3.3, the red one is just a little higher. 37.6 is a little higher than 37.3. They're very close together. So we're comparing the approximate value, 37.3, with the actual value. So whenever they tell us to get an approximate, we plug into the tangent line because that's an approximation to the real curve. When they say approximately equal, we know we're plugging 3.3 into, you might say, well, you didn't plug it into F. No. When they say approximate, I don't plug that 3.3 into F. I plug it into the tangent line because that's the approximation, the shaky equals. That's the approximation to the original function. But when then they say actual f of 3.3 with the true equals, right? This equals here. This means true equals exact value, not approximation, right? Not approximation. Then I plug in to the original function. So you got to understand what's happening. We're using the tangent line as an estimate to the real function. And you can tell they come out very close when you're around the intersection point where the tangent line intersects the curve. And so there we go.